So it was a good opportunity, the holiday today, and getting to interact with you students. Good morning, all who have joined in, and hope you enjoy this 40 minutes session. Uh, I think most of you are from a aero background, so I will be talking about flight controls, but I may skip on the surfaces and things like that. But the slide that is provided has all these things. I will quickly run through as a just for the completeness sake, I would say. Okay. So I'm going to talk about flight controls and what we systems engineers do. Very clearly, I would like to mention systems engineer because I would like all you engineers to grow as systems engineers tomorrow. Nowadays, you are either electrical engineers or electronic engineers or aerospace. But then when it comes down to it, every one of you is building a system. So I would rather have only one subject called systems engineering, and all of you should aim to become a systems engineer. So I would like to give a perspective of what systems engineering is, and when I walk you through the different phases of flight controls, you will understand what all different things that happen. Okay. So just a disclaimer that these are my views, and the company I work for, that is Honeywell, and Incosi again, because I'm a member of Incosi, they are not endorsing any of these views as such, but it is my views, and I am giving it as a knowledge gain for you, so please use it. I think Professor has already covered this. I will skip this. Only thing is, I am a adjunct faculty at Manipal University as well as NITK Surathkal also. And I love interacting with the students, and whatever experience I have gained, if I can share it with the younger generation, I would be very happy that I have contributed something. So today we are going to learn from Wright brothers, and I can't have a question and answer sort of discussion, but Wright brothers are the two people who made the first flight happen, and a lot of things they did is what we do today also, right? They were purely mechanical. We are into an electronics phase, but we do a lot of things that what the Wright brothers did. Okay. These are the takeaways. I will give a glimpse of what a system engineer does in flight controls, and I will hopefully you will get a feel for the complexity of the system. You will gain knowledge of how an aircraft flies, what is a control system design process, and more so what at a B and ME level that can be done in flight controls. Okay. So the story of flight, actually, these are lovely videos. When I do a face-to-face session, I play these videos. They're very interactive that way. But we are not having that things. It's a PDF here. This is a very funny video which says how man wanted to fly like a bird, and he used to jump from a cliff, and a lot of people died that way. But that is how the whole thing began. But then they had this glider. So what you see here is Otto Lilienthal, and he is the first person who actually successfully flew a lot of these gliders. He made the glider and flew it, and his story is very very entertaining, as well as you can get a lot of knowledge from that. And the Wright brothers actually read his books, read his data, and they worked on that, and that is how the Wright brothers could fly. But the base was what Otto Lilienthal did with the gliders. These are some of the very funny, aeroplanes that they tried to develop. They said, okay, this aeroplane is very heavy. Bird has only 2 wings, so let us have many wings so that we can maybe fly better. Okay. You can look at the QR code here, scan using your mobile, and you can go to those websites. Okay. These are some of the early concepts that you have. These are some lovely videos on and very funny videos on what all they were doing, and you would really see how they wanted to, how desperately they wanted to fly. You can look at some of these videos, and it's really funny, and but it tells you how these people were thinking those days, and that is more important. And then we have the first flight on December 17, 1903. We have the first flight by the Wright brothers. A heavier than aircraft took off and landed. More so, it landed. That was more important. Okay. And where are we today, right? So we have these forward swept wings. Okay, the X-29. Absolutely new concept. Everywhere you see aircraft with wings, swept backwards, but this is the other way around, and absolutely unstable aircraft, and it can only fly because of flight controls. Okay. This is our Indian LCA, and something I'm very proud of, because I was working on this since 1995. I worked on this aircraft, and it's really a proud moment that it could take off, land, and it can do beautiful maneuvers. It can do weapons delivery, and it has been accepted by the Indian Air Force. So why is flight controls important, right? The primary thing is that you see the vehicles, right? You see a bicycle, the car, and all that. One thing is it is on ground, but then the control is important because that is the only way you can steer it and go from one place to another place. So the forward direction is easy, your engine does that, but without a control, you can never go to your destination. And that is the most important things of flight controls. That flight controls has one more dimension, that is the height. So not only has the aircraft to do the XY direction, but it has to do the Z direction also. And that is the only way, because of the controls, it can fly across the oceans. So this, I would say, was the key to controls. If you see, this is a piece of cardboard, and the Wright brothers used to have these cardboard on their tires, and so one of the brothers was moving it around, and the other brother was watching this, and then he realized that he can actually control the aircraft in a lateral direction by twisting the wings. So if you see the Wright Flyer, it actually has that. Okay. And this is the Indian light combat aircraft, and it is unstable longitudinally, and it has something known as a fly-by-wire, a control system that was tested, designed, tested, and coded, tested. Everything was done in India, and it is flying today. So quickly run through these slides. How does an aircraft fly? So an aircraft flying is actually a balance, I would say, of forces. So the drag force, which is there, which is the air obstructing the big aircraft, and having a force which is actually pulling it, tiger by the tail, sort of pulling it backward. And to counter that, you have the thrust, and you require engines for that. And then you have the huge mass and weight of the aircraft. That has to be counterbalanced by a lift. So the lift balances the weight, and the thrust balances the drag, and that is how the aircraft moves up and down, or goes forward and backward. Not backward, sorry, forward. So for the thrust, you have the Wright brothers engine. So you can go to this website, and this is what they used: a petrol engine that could run the propellers. And then you have this jet engine, and this website link tells you how a jet engine works. You can go and have a look at that. So basic thing is the air comes inside, it is compressed, and the fuel is injected and burned, and that is pushed out, which again rotates this turbine, and this is a cyclic process that gives you the thrust. And then you have this angle of attack. Aerospace people are very well aware of it, that you need to have this tilt, and this tilt is known as the angle of attack, and the people who are love kite flying would realize that they have to tilt the kite in a particular manner, then only it climbs up. So an angle of attack is the most important thing there. And then you have the the movements. That is the pitch, the roll about the x-axis, the pitch is about the y-axis, and the yaw around the z-axis. So these are the three movements of the aircraft, and these needs to be controlled. And to control this, you have these surfaces. So the aerospace people would be aware of this. So you have the elevators for the pitch control, ailerons for the roll control, and the rudder for the your directional, your yaw control. Okay. And more than the surfaces, you have so many other secondary surfaces. Okay, so elevators, rudder, and the ailerons are the primary, but then you have the slats, the spoilers, the flaps. Okay, all these are also required to be controlled, and today's control systems on all these modern aircrafts control all these things electronically. And that is where I would say Honeywell, you control system designers, you avionics engineers, or electronics, software engineers, they all come into picture because of these things. Not only the primary, but all the secondary surfaces that need to be controlled. Okay. A close look at some of these surfaces. I'm going to skip these slides. Okay. You can look at wiki for all these and know more about it. So what is basically flight control? Okay. Flight control in this video, and it tells you how a pilot controls in the three axes, how he moves the pedals, the the joystick here, and the how the surfaces move. So this is a beautiful video that you could look at to understand flight controls. Okay. These are the mechanical control systems. So you see those wires here. They are actually wires which go through tubes and they move the surfaces in smaller aircraft. It's just like your bike. Okay, and the cables are very similar. Okay, to the bike thing. So, and that is what is used to control the aircraft. Very surprising, but exactly similar things to the bike control. And then you have the assisted control. So as the aircraft becomes bigger, the surfaces become bigger. So you need to have some hydraulics. So you do have, the cabling and all. It goes till the end of the aircraft near the surfaces. But then again, it moves the hydraulics. But it is again a mechanical control systems at this. It is assisted. Hydraulics moves the surfaces because they are very heavy. But it is more like your poclanes and all that, shovels that are used to digging, pretty much similar to that. Okay. And then you have the fly-by-wire, which is a pure computer control. So you remove all the mechanical linkages, everything not required. You have the hydraulic actuators, and then instead of the mechanical links, you completely put wires there, and they move the surfaces, and the control computer is executed by the pilot, and then you have a fly-by-wire system. So this is a beautiful video, which unfortunately cannot be played here, but it actually tells you the story of a fly-by-wire. Okay, and you can look at this video later and actually see how the fly-by-wire works. So I have a small, a slider on that. I will walk you through that, but this video explains it much better. Okay, now this is the first fly-by-wire F8C, which was converted to a fly-by-wire system. And what you see here, the computer, this is actually the lunar lander, computer that Neil Armstrong flew with. So that computer was used here to make the first fly-by-wire system. And today you have fly-by-wire in all these aircraft. So this Dassault Falcon has a fly-by-wire system. Okay, and it is a business jet. People use it. Uh, Maybe fly-by-wire is not required, but they use it as a prestige questions to have a fly-by-wire aircraft, perhaps. So that is how advanced we are today. Okay. I think this is something that every control engineer should know. What is stability? What is positive stability? So it is a curve, and the ball will come back to this center point in case there is a disturbance. So that is known as a positive stability. Then you have the neutral stability, a flat surface, and the ball can roll away. And then the negative, which is a unstable sort of thing. So this is something, if you understand, you understand controls to a large extent. And this is the fly-by-wire I was talking about. So you have quadruplex channels. You have 4 channels four computers, all four sensors. So this is the kind of things which is there in the Indian LCA program, and all of four because of redundancy, because there is no backup here. So if one computer fails, the other three will work. If two fails, another two will work. And perhaps he can't fly it, but at least he can land the aircraft. Okay. So this is how a actual architecture looks like, and this is an electronics domain. It is not an aerospace domain. Okay. And then you have some lovely videos on accidents. Okay, I should not be calling lovely, but at least the pilots didn't die there. So I can perhaps still say they lost an aircraft. And all these are lost because of control designers not doing their job properly, I would say, or they missed out something. Okay, so you can look at some of these videos and really see that how important it is that a control system designer do his job properly. Okay, this is a video of the another accident, and this is there known as a pilot in loop. Okay, the pilot is flying the aircraft, and if he is trying to pull up and the aircraft is slightly delayed, okay, it is not pulling up fast, so he may be pulling up more. Okay, then he says, oh no, it is too much, so he tries to push it down. So this situation can become unstable. Okay, and this is something we need to be very careful about. Okay. So now that we know how important control is, we know that how an aircraft is controlled by the surfaces. Now let us see how it is designed. Okay, I'll spend some time on this. So this is the beautiful thing that I'm very proud of. This is how we actually go about systems engineering process of making a aircraft flight control system. So you have a flight envelope, and this has as an x-axis, it has the speed. As a y-axis, it has altitude. So this basically tells you where an aircraft is going to fly. Okay, it can't fly at very high speeds on ground. It can't fly at very low speeds in air. Okay, here I would be asking a question why, but I will perhaps answer you today. A high speed here because of the heating actions and the air resistance and things like that. So on ground, because the density of air is very high, he can't fly fast. In air, he has to fly fast, because otherwise he will, because the air density is low, he will not get a lift. So he has to fly at a higher speed because he has to maintain the lift. Okay, and this is the basic profile of a flight envelope, and we make a lot of linear models. You will see this. Remember these steps. So you have a flight envelope, you have a lot of linear models that need to be made, and once that is done, we have to have these requirements at a very top level that tells you what should be your control design parameters. Okay, what should be your rates, what should be your margins for controls. Okay, how fast you want it to respond, how stable you want it to do, and then you do a lot of non-linear. So at a college level, you may perhaps only study perhaps in your fourth semester linear control, but then you will have to do a lot of non-linear control also. And this is what is done, and a lot of simulation is done, and we will see in the going ahead slides what these mean. So this part is mostly done by the controls engineers and the aerodynamics people, the aerospace control people, and all that. So they need to know the aerospace here, and that is one aspect. On the right side is all about coding, testing, and electronics. So this comes into your electronics engineering domain. So you need to know flight controls coding, you need to know the algorithms, you need to know FPGA, you need to know the processors, how do they communicate, you need to know how to write C code, what is embedded software, what is operating system. All these things come to the right side. Okay, and Honeywell is very good at the right side. We do have in USA people working on the left side, but mostly we do work on the right side. Okay, at least in India, we work on the right side. A lot of linear control also happens in India also, but may not be for ACRA, but for other systems. Now we will walk through one by one. Okay, I'll quickly run through. About 20 minutes done, halfway through. And so first thing is to make the linear model. Okay, And these are the equations. Okay, so very easy equations to understand. And basically, it is x dot is equal to ax plus bu, which is your state space equations. Okay, and you have the three forces, the accelerations, and the three moments. Okay, so UVW and PQR. I think the aerospace guys know this. Otherwise, this is the only maths that is in these slides. Okay, you can skip all this and not worry too much about it. But if you are in this field, you need to know all these equations. Very important. So where do you get all the data for this? Okay, the Wright brothers. So this is what I was trying to correlate between Wright brothers and what we do today. Okay, so the Wright brothers had their wind tunnel, and they had this beautiful sheet of paper where they actually moved the surfaces and figured out how much of a lift is happening. Okay, now what you see on the right side here is the Indian LCA model inside the NAL wind tunnel. Okay, at Bangalore, and the same thing is done. The data is prepared, but the data is in a computer domain. Okay, and they are all files that we use. Okay, and this is wind tunnel. This is again a video of this. So this is the flow, and you can see the flow there. And as the the surface is rotated, you can see how the flow changes. And this is a homemade wind tunnel. This is made by my son and his friend as a 12th grade project. And they could actually demonstrate the smoke on a surface and took some video and all that. So I think it is not, very high funda, I would say, right? Anybody can do it, right? Wright brothers could do that primitive things. Students can do it in their college and actually, figure out some of these things. So these are made with straws here to get a laminar flow. Okay, and then we have the computational fluid dynamics. So aerodynamics people working in mechanical domain, they would perhaps know what is a computational fluid dynamic. So this thing generates the flow and the lift parameters and other coefficients using computer algorithms. Okay, there is a lovely video here on computational fluid dynamics on YouTube. You can get to know more just by going through that. Okay. Why are these things required? They give you actually the coefficients that you can use to model. Okay. And how many models do you require? Okay. So in the Indian LCA program, we generated 2 lakh models. And it used to run on 10 PCs for a week to generate our data those days. Okay, I'm talking about 1995 time frames. Okay, and this was our flight envelope sort of, and so many models were generated to test the control law. Okay, that is the kind of complexity would be involved in the industry. Okay. And this again is the flight envelope, tells you the loads. Okay, so different ways of looking at the same envelope. Okay, so if you want to know about this, sorry about the title there. If you want to know more about it, you should know numerical analysis. You should know differential equations, mechanics, kinematics. Okay, when I'm talking about all this, you will say, yeah, I studied all these things. I studied in physics, I in PUC level or 12th level, I studied in first year, and I have conveniently forgotten. Okay, you should not forget all this. So these things are very important if you are going to be in this field. Okay, basically the first chapter of your control system textbook that talks about modeling. Okay, mathematical modeling. The very first chapter is all that is done in the left side. Okay, so you will see how important that is. Okay, you need to know MATLAB Simulink, very important. You need to know basic aerodynamic. You need to know mathematical modeling. Okay, and these are some of the books that you can read, available online. Okay, and you can your libraries would be having it. Some very good books here that would help you learn this field. Okay. Next thing is the design and analysis. Okay, so design and analysis, you need to actually make this. So you have an aircraft, which is a plant model. You have your compensation design. You have a forward design, and this is what I was talking about. You have the pilot in loop oscillation. This is because of this outward thing. Okay, the pilot is in outside loop, and he is trying to control the whole system together, and he is looking at motion and visual cues. Okay, and so this is actually your complete control system. Okay, looks very simple, but it can get very, very complicated when you get into the nonlinear. So if you want to know these processes, you need to know all these things: Bode plots, root locals, eigenvalue computations. Okay, all these are very important. Okay, and you want to look at all the critical areas in the flight envelope. Make sure that all the the aircraft is trimmed at those zones, and then you can do some small perturbation models so that you know that they are linear in that small zone, and you can design a control system. Okay? And this is kind of complicated. So this is the X29 controller from this paper. Okay, a lot of nonlinear things. The Indian LCA controller also looks something very similar. Okay, and this is a Boeing control system, only the lateral electronics, and this is made by Simulink models. Okay, 50,000 small elemental blocks connected by about 1 lakh lines, about 400 inputs. So I'm just trying to show you the complexity, how it increases maybe from a college level, textbook level to an industry level sort of thing. Okay, and this is the aircraft that flies. I have flown on this, no issues. You can also fly it. I have flown it as a control system. May not be a designer, but a tester. But my team made these models. The 50,000 element model was made by my team in Bangalore. Okay. So there are a lot of control system design methods, optimization, right? I understand that optimization is taught, but not a control system optimization may not be taught at a college level. So MTech level, I have done this in Manipal, and people have used this optimization in their MTech projects, done very well. Uh, and you need to do a lot of conditions. It's not that one single condition. If it is a fighter aircraft, you drop the bombs. So you drop the bombs on the right side. The left side is still having the bomb, so it is heavy. Okay, what happens to the roll? Okay, the whole plant dynamic changes. What happens when the aircraft is flying at a very high altitude? Whole dynamic changes. Okay, so lots and lots of work is involved by the industry to do all this. Okay, there is something known as aircraft flutter, which has to be taken care of. Okay, go through this video. It's basically the whole wing, it moves around when the aircraft flies. Okay, and it moves up by about maybe 10, 15 feet or so. Okay, for a 787. Okay, it's not simple. Okay, you can I think look at, there is a video link I would give. This is the Indian LCA. Okay, so what they did was that the rubber cords lifted the whole LCA up and injected vibrations at the surfaces. So the whole aircraft is to vibrate. Okay, and once you do that, what you get is a frequency response. So this is the frequency in hertz and the magnitude, and you will find points where the aircraft actually vibrates. Okay, so these are known as structural vibrations, and you need to design notch filters to remove those vibrations. So it's very important that you design notch filters. So some of these things are not taught at a BTech level, maybe at a PhD level perhaps, or an MTech level to some extent, I would say, if you are into aerospace. Okay, so this is what is done. Okay, but industry, it is very, very important. So to know all this, if you want to do these things, you should know the controls theory, you should know root locals, digital control system, PID compensation, block diagram reduction, and the remaining chapters of your control system textbook. Okay, this is what is required if you want to come to this level. Okay. Now you do a lot of linear, non-linear simulation. So you basically do it on, your PCs. But then there is an analogy with the Wright brothers. Okay, Wright brothers didn't fly their aircraft. Okay, they made kites, and they didn't have computer those days, but they made kites and they simulated the whole thing. Today, the same environment is available as a computer for you. Okay, this is the MathWorks tool that is available, and you can actually visually see that aircraft can be landed and things like that. Okay, and what you see here is the simulation results with an actual flight, and you can see the match. The match is so beautiful, right? So the simulators are of that high fidelity. Okay. And if you want to come to this level, you need to have these, the numerical analysis, kinematics, and the algorithms. Algorithms are very important if you come to this level. Okay, and you require to know system modeling concept. Okay, so this is what you come down, and then we do the pilot evaluation. Okay, so the simulation is done. Now the pilot has to fly. Okay, so this is a NAL, the simulator, and I have sat in this so many times. Brings back very fond memories. And the pilot used to actually fly this, and he will tell you. So we had given him a patch panel, and he could change the gains. Okay, he says, "Yeah, I'm very happy with this. I'm not happy with this. Okay, increase the gain, reduce the gain." And he used to really get involved in the control loop. And he used to tell, because it is not only important that you make the aircraft stable, you want to make it very, very what I would say, comfortable for a pilot to fly. Okay, because remember that the pilot is in the outermost loop, and if he is not comfortable, he can make it unstable also. And then you have these some of the bigger simulators. So you have these whole surface that is moving. Okay, the pilots actually, they get trained on this. A very costly affair. Hour of pilot training on this is very, very costly. Okay, and I think if you are aiming to become aerospace pilots, you all your money actually goes into some of these things. Okay, but then you do have very good simulators. So we have such simulators in Honeywell, not the motion type, but other desktop simulators. And people are actually the people who come here, our interns and all that, and the young engineers who join Honeywell, they get trained on this. NAL has some lovely facilities for this. Okay. Having done this is something very important. Okay, the basic simulator is very low cost, what you have in your laboratory perhaps. And in realism, if it is not very close to the reality. Okay, and the final prototype has the highest cost and the highest realism. Okay, somewhere in between you have these three: the handling quality simulators. For the Indian LCA, it was there at the ADE, the lab in Bangalore. Iron Bird was at HAL, and in-flight simulation was done in US. Okay. Now, what is in-flight simulation? I will come to that. In-flight simulation is basically a F-16 aircraft where we change the control and the dynamics to behave like LCA. Okay. You can see this video of a flight simulator. Okay. And this is what is done. So you have the F-16 dynamics, and you change the dynamics by actually removing it, and then put a LCA dynamics on top of that, and then you have the LCA flight controls here, and you actually fly the aircraft, but it is like flying LCA, I would say, because the whole thing has been changed. Okay, a very costly affair, but it gives you the confidence that what you have done is good. Okay. And finally, our design is done, and we have lots and lots of documents. Okay, we have data tables, we have the design block diagrams, we have Simulink models and all that, and a lot of text in English. Okay, we describe all our design in English, and then it is supposed to be implemented on the onboard computer. Okay, so this is aero domain, the controls domain, and now we get into the electronics domain, the electrical engineering domain, and the software engineering. Okay, so this is into digital control. So not only do you have to know the flight control system, the algorithms, you need to know all this. What is the sampling frequency? Okay, how do you connect it to the sensor? What is redundancy? Okay, what is voting logic? I have three sensors, one sensor failed. Okay, what do I do with the two sensors? Okay, how do I know that a particular sensor has failed? So that is redundancy and voting. Okay, how do I do real-time coding? Okay, what should be my scheduling? Okay, I will schedule the critical things very fast. I will schedule the other task very slowly. Okay, nowadays we have automatic coding. Okay, we just make blocks, and we do an automatic code from that. Okay, how do you bring in the fault resistance? How do you bring in error handling? Okay, how do I test my computer on its own when it comes up? Okay, what are the built-in tests that you have? All these things have to be done. Okay, and this is why I say that you require to be a systems engineer. I should know as a software engineer what is electronics. I should know as an electronics engineer how to write a C program. Okay, very important that we know all these fields. Okay, and this is a state chart. Okay, for a very simple autopilot, this is a state chart. Okay, and actually the state charts will be bloated up. Okay, so if I write a C code for this, I will have 500 odd if then else statements for a simple autopilot of an aircraft. 500 if then else statements that has to be tested. Okay, coded, tested, and made sure that there is nothing wrong with that. Okay, and that is how I got into this formal methods domain, where I mathematically prove the correctness of the system. Okay, so that is something the software engineer would like to perhaps get into. Okay, and then you have to have a architecture. Okay, so this is the pilot controls here, and that goes to the computer systems, and that goes to all the actuation systems. Okay, the feedback comes back, and then there is a display panel. The whole aircraft control system is, complicated. This is a simple thing I would say for a business jet, and when you scale it up to a Airbus A350 or a Boeing 747, it really scales up to a very big thing. Okay. And what should you know if you want to get into this field? You should know algorithms. You should know C or another language. Okay. You should know the real-time principles. You should know digital electronics. You should know FPGA. You should know what is an NVRAM. Okay. How we code that low-level programming. Okay. How I address the memory. What are digital bus protocols. Okay. Link labels. All those things are required. Okay. The picture that you see is a beautiful digital fly-by-wire that flies the Indian controls, and you see the number of cards that are there. If you see your PC, you have just a single card. On your laptop, you have a single card. So here you have about 16 cards. Okay, and this actually flies the Indian LCA. Now that you have done the coding and all that, you need to test it. Okay, and most of the jobs in India are because of this. So don't belittle this that I'm a tester, I'm not a coder perhaps. But testing, you should know everything what I have taught you earlier, as well as you should know principles of testing, the different levels of testing. So we have low-level testing. A lot of model-based testings are done. Okay, and white box testing is done. We call them as low-level testing, where you look at the code and you try to figure out how to test it. Okay, we have a high-level testing or gray box testing. So we have a black box testing and a white box testing, and we kind of know what is inside, and then we have a high-level requirements, and we test them. Okay, and then we have a black box testing where we don't know what the code does, but we know what the behavior is. Okay, and then we do the final testing. So if you look here, this is a very famous thing. We call it as a V model. We start with requirements and we end up with perhaps flight testing. Okay, and these are the different levels of design. You have a high level design, you have a low level design, you have a coding, and then you make your system. Then you have a unit level test, you have an integration test, you have a system test, and then you have an accept test. Okay, the C people, they know all this. The computer science guys, they are very aware of it, but I think the avionics guy also should be very well aware of it, because this makes a lot of money for the Indian industry, and a lot of testing happens in India. Okay, this is the model-based testing. We use it extensively. I was happy to be involved in this too, and I think in India we were the ones we started it for the Indian LCA program, and a lot of other projects started using this. So we have a model of a system, we have a control system model, and we have the flight controls model. We gave the same inputs here, and then we compare the outputs, and if they match, we say that both are good. Okay. Even yesterday I have done this. Okay. I do it every day. So this is something that works for us. Okay, very well. And then you do the system tests. Okay, and they are done at something known as Ironbird. Okay, and this is the Indian LC Ironbird at HAL. Okay, and this is the Ironbird for a Airbus. It's maybe a 6 or 7 story building high. Okay, what this has is all the actuations, all the actual electronics of the whole aircraft on ground. Okay, and the actual electronics is there, the computers are there, and the pilot can actually fly this and move the system, so to say, on ground. Okay, and then we do the final flight test. Okay, this is the Indian flight test, and uh, this is the a lot of people who have retired actually, and so they used to fly this. So this is the monitoring station, and this is the Indian LCA, and that what you see behind is a chase aircraft that actually goes around the aircraft to check if there is any leak, something bad is happening or something like that. Okay, and then that is for the LCA. But for a bigger aircraft, we have tests like this where they freeze the whole aircraft, or they run it through a lot of water. They do takeoffs with a very high heavy weight. A lot of tests are done. Okay, and then this I like students like this. This is a chicken gun test. So they used to actually fire chicken earlier days, and then once the chicken was fired, they used to cook in the mess. The same chicken used to be cooked and given as a dish. Okay, just joking, but that is what used to be done earlier. They used to actually fire the chicken. Nowadays, of course, you don't fire chicken. You fire rubber pellets, which has the actually the same weight as a bird and is as soft. And this is hit against the windshield to make sure that something like this doesn't happen. Okay, this is a bird hit on an aircraft, very dangerous. So even in the Indian LCA program, we had this. The bird hit the surface, and we had to do an emergency landing because the surface there was a dent. Okay, and then we do this lightning test. Okay, we actually send in a lightning bolt onto the aircraft to make sure that the system works right, and the aircraft can fly in the clouds. This is very, very important. Okay, so this was for the LCA, but use the same thing for the aircraft, big aircraft also, Airbus A350 in a lightning test center. Okay, most of the things are done. Okay, the Wright brothers didn't do this because not much of electronics was there. I mean, zero electronics was there, I would say. But today we need to do this and make sure that the electronics actually works with these lightning strikes. Okay. So if you come to this level, so you need to know the testing techniques. Very important. You need to know what is the hardware. You need to know what are the different scripting languages. Okay, we use Python. We have our own. Honeywell has its own scripting language. Okay, so we write our test scripts in that. And you need to know maybe a bit of controls. May not be very heavy into controls, but you need to know a bit of controls. But something I would like to emphasize here, that as a test engineer, you should have the guts to tell your boss, perhaps who has designed the system, that you are wrong. Okay, very, very important. So this comes to your engineering ethics, right? You learn ethics in your final year, and you say, what is this? Yeah, English teacher comes, teaches ethics, and but as an engineer, it is binding on you to ensure that you tell the truth, make sure that your boss understands that there is an issue. Okay, and you don't do things what happened, your recent Boeing 737, 1 year up, and the aircraft is still not flown. Okay, there were major issues in the control system, and people should have been told, right? And that was not done. Okay, so that is very important. As a tester, it is an ethical question for you that you do it. Okay, last few slides for me, and this perhaps you will like. You can go through this video. It talks about certification, beautiful how different things are tested. And finally, an aircraft has to be certified, and the in USA the FAA has to approve this. Okay, then only the passengers can get into this. You can watch this video. It talks you through the steps of how an aircraft is certified. Okay. So what can you do at your level? Okay, so this is a project done at a B first year. A paper is also available there on how to do PID controls. Okay, and you can watch this video. So this has been done by my son, but he could make a PID control. Okay, and he could implement it on a small Arduino board. He could use the gyro sensors, and the whole thing could be done. Okay, something very interesting. So any BE level student can do that. Okay. Idea is you should know what is electronics, what is PID control, and what are the sensors, and what are the algorithms. Okay. And this is done in, by B graduates, interns, and graduates who joined the company. And they made these things using Simulink. And this is the flight gear you can do at a BE level. Okay, get flight gear, get a Simulink model, make a small panel here. This is also made in, MATLAB, and you can actually fly it in real time. Okay, and this has been done by fresh graduates who have just joined the company, maybe 1 year into the company. So it is very easy to do it. I'm not saying it's all very high funda. Okay, we don't require a B level, a PhD for this. Okay, anybody can do it, and I think this is something that could be done in your college. Okay, gives you a lot of insight. Okay, at a higher level, at an ME level, I would say you can explore a lot of things. You can explore optimizations, you can explore different metrics, you can explore how a thing is coded. Okay, and test it. Okay, what are the new design methods that you have? How do I optimize a controller? Can I use genetic algorithms to come up with a optimal PID control? Okay, so Manipal, this particular student had done that, and she used the optimization that I taught in a session like this, and she could do that. Okay, all these papers have been written by students. The first student is me during my PhD time, but then of course all others are students who have written these papers at I would say at a MTech or a PhD. Okay, so this is something that you could perhaps do. Okay. I would encourage you to look at INCOSI also, right? As I think I personally feel that all of you should grow as systems engineers. And one of the ways to become a system engineer is perhaps to join some of these organizations, right? You are IEEE members, you are members of, the Institution of Engineers and all that. But INCOSI is all about systems, okay? It is a world body where you could interact with experts in systems engineering, not only aircraft, but in automotive domain, electrical domain, biology, medical, all systems. Okay, and we had a conference here last year, yeah, organized by INCOSI. India chapter was, did a major role in that, and we actually gave out passes to a lot of students who had visited us. It was very nice interaction, and students really enjoyed it. Okay, so this is something that could be done. You can visit the INCOSI website. We have certification at a very low level, but you require a BE for that. So once you finish your BE, perhaps you can give the INCOSI exam and become the member. So associate member, we start with the associate member, and then you can grow higher as you become. So it basically tells you that you are a proficient systems engineer than just an engineer. Okay. So if you are interested in this, you can get in touch with us, and you can get to know more things. If you want to start a student chapter, perhaps at UPES, we can help you out with that, and we can do webinars and help you out to get certified. Okay. But main thing, I would like you to grow as systems engineers. Okay, more than anything else, I would want you to become system engineer as you go forward. Okay, 15 years down the line, you should see that you are a systems engineer. Okay. My final words, okay, on December 17, 1903, it was a stepping stone, okay, for mankind, and the Wright brothers flew the aircraft. Today we have aircraft breaking the speed of light, the height records, okay, and 100 years ago, two-member team challenged the nature and flew a heavier than air, man-carrying vehicle in a sustained flight for the first time in history. Okay, India today has a team of control engineers. Okay, I'm not talking about the US. I'm talking about India. I'm talking about engineering institutes in India like UPES, and people like you who are aeronautic and software engineers who can contribute to this. And they have contributed. They have made the fly-by-wire, the Indian LCA program. They have made an unstable airframe stable, flown it, okay, with all the required handling qualities. Okay, I would leave you with this message. Would you like to be one of them? Thank you very much. And you can look at my website here. Only thing I will ask you is, because I find that a lot of people ask me for internship and jobs. That is the only reason they contact me. I cannot do much about this. Okay. So I would pray that you don't send me mails asking for internships or asking for a job. If you have done well in whatever you have done, if you have a very good LinkedIn presence, if you have YouTube videos that tells you what you have done, and if you have a very good resume, you will definitely get a job. Okay, you don't have to have people taking you. Okay, so with that message, I would close my talk today. Any questions?
Thank you, sir. Thank you so much for your talk. Now students can ask the question in the chat box.